Thank you so much, Dr. Avicii. I am Sanchit. So just a quick introduction to Professor Steingart, who is our esteemed speaker here today. So Professor Steingart is the Stanley Thompson Associate Professor of Chemical Metallurgy in the Department of Earth and Environmental Engineering at Columbia University. And he's also the co-director of the Columbia Electrochemical Energy Center. Through various aspects of his research, he is basically research around materials, energy, storage, batteries, and has formed 5 startups in that process. The latest of which is feasible, which is fascinating. He joined Columbia recently. He used to work at he was at Princeton earlier and at City University of New York, and he holds a PhD from the University of California, Berkeley. I welcome Professor Daniel Steingart.
So while I'm waiting for the clicker, I just want to thank Ravina, Sanchit, and Brenda for a wonderful week. This is my first trip to India, and it's been actually packed. 3 cities in 4 days. And I thought I was coming in the spring. In the U.S., this is like the best time of year. Yes, so jokes on me. But I hear that this is a dry heat. This is okay. Spend enough time in Phoenix to know that joke or that lie we tell ourselves. So, in any case, it's been wonderful getting a very brief sense of the opportunities and challenges in India. It's easy for me as a battery person in an air-conditioned lab to try to invent some chemistry that seems to work okay on our bench. It's a very different story to have something withstand 40 degrees C weather for 10 years. And this is really the goal, as Ravina so well put. So thank you for giving me your Thursday afternoon. It's really great to see so many folks here. And
Dan, we might need to readjust the mic because
okay.
It's not very audible.
Okay. Is that better? Yeah. Okay. Thank you for giving me your Thursday afternoon. We're going to talk about why energy storage is so hard, but why ultimately I'm optimistic. So it's going to take a very optimistic, future-looking perspective. It's going to get really depressing for most of the talk, and then we're going to end really strong. So let's do this. What is this? Right. And so, what is the most amazing thing about Star Trek? Right, so that's what every good student says, and that's incorrect. It's really important, it's super important, but it's not the most amazing thing about the world of Star Trek.
The reactor.
Right, dilithium, almost. We're getting there, but not quite.
Solar panels?
Almost. The most amazing thing, and this is not fact, this is my opinion, but this is sort of what drives me. The most amazing thing about the world in which Star Trek takes place is on Earth, no one wants for anything. It's what they refer to as a post-scarcity economy. And because there's a post-scarcity economy on Earth, we can do wonderful things in the world of Star Trek, like explore the universe. Everyone on Earth is happy, and it's so taken for granted, they don't talk about it all that much. So then what can we do as engineers and politicians and just people to get to a post-scarcity economy? I'll posit that there are 3 things we need. production, distribution, and storage. And so if we look at the history of agriculture and we follow the growth and strength of civilization, the ability to reliably grow food, reliably distribute it. And so when I lived in New York previously, I lived a block away from this thing called the food co-op, where we loved our food so much we decided to actually work there to make our food cheaper in New York City. I'm not sure I would do it again, but it was an experience. And then this is perhaps the most boring thing, but the storage silo and the ability to preserve food allowed us to get through stochastically poor aspects of generation or distribution. Having storage near the point of generation and near the point of distribution makes life healthier. This is not a solved problem, but we see what the solution looks like, and we've done a remarkable job of getting there. I'd argue that simply in the world of capital, the ability to generate items of value, store their value in the form of money, and distribute that capital, when this machine works cleanly and fairly, the world is a better place. So where are we with energy? I'm really happy to say that we're nearly free with solar panels. And there's still challenges and there's still technical hurdles to overcome, but we're really close. And the distribution grid, well, I have to be careful what I say here. In the US, we take it for granted that it works well. And in India, you have more of your own storage in basements. The lead acid battery is this hoary artifact that provides some semblance of stability in poor periods of distribution. In the US, that's not really the case, and the best we have are these large pump hydro facilities, and we've built every dam, every map we're basically allowed to, and most of these pumped hydro facilities don't exist to support solar, but rather they exist to make nuclear safer, because nuclear plants like to run flat out, steady state, they don't like to ramp up and down, and so when we have too much energy, we pump it up a hill, and when we don't have enough coming out of the nuclear plant, we extract it from a turbine coming down the hill. So why is this the best we have, and why is the best you have a lead acid battery that doesn't last all that long in your basements right now? As Ravina said, storage is hard. If it wasn't hard, I wouldn't get to be a professor at Columbia studying it. I would have to be in the real world actually doing it. So I get to sit on a fairly lofty perch and talk about why it's hard. And some ideas we have about how we can solve it. So this is why I think storage is inherently hard. Remember that it took 10,000 years to get to a point where we are almost at the point where we are without hunger. Almost. We're not there yet, but we're better than we've ever been. It took 10,000 years to get to this point. I teach this course called thermodynamics. Everybody hates it because it's depressing, and it's notoriously hard. It seems like it's really easy, and then it takes a left turn at entropy, and everybody hates it. So, but that said, I've had to teach this course like 20 times, and so I think about energy a lot. And when I think about energy, you realize that all energy is the same. Whether we're using it to feed ourselves or we're using it to charge our devices, all energy ultimately comes from the sun or the earth, and we convert it chemically into food, which we eat, or we convert it into electrons that power our devices. And to date, over the past 200 years, our devices have required an operating power between 0 and 100 watts, roughly. Your laptop is 100 watts, things that are battery powered. Batteries are tried and true here, they work really well. Every once in a while, we try to do something that's not batteries in this space for portable devices, and it simply has no market acceptance. Because batteries are fine. We are the cutoff. We, as people, are the cutoff because when we think of a 2,000 calorie per day diet, if we divide that by 24 hours, we get 100 watts. So this is a depressing thing or a beautiful thing, depending on how you look at it, because this means that 10 LED light bulbs has the same thermodynamic imperative on this earth as you do. You are worth 10 LED light bulbs. So does that mean the LED light bulb's worth a lot or you're worth a little? I can't tell you, I'm not a philosopher. I can just tell you that that's your energetic imperative. And when we think of our living spaces, we quickly need more energy to be comfortable and happy than we need to survive. So a given 1,000 square foot room or apartment needs about 1 kilowatt to run constantly between refrigerator, air conditioner, lighting, other aspects. And with transportation, it's even worse. So to rephrase this a bit, 2,000 calories get you a healthy day, 10 light bulbs running for one day. Say, okay, turn the light bulbs off, 5. It gets you an air conditioner for an hour and a half. And it gets you maybe 13 kilometers in an EV. And so we're at this point now where electrochemical engineers are being asked to compete with or do better than the food supply. Now, we can try to use less energy, and this is a messy, problematic plot, because the best we can do to understand how much energy we ought to be using is something called, and what we should be using for is something called the Human Development Index. And the Human Development Index is largely subjective. It has some economic and physical quantities to it, but it's this composite index that basically says how healthy are we, how long are we living, how productive are we. And we want to be as high as possible on this index. No one's at 1, but this is what we aspire to. And there's this strong correlation for low amounts of energy use with climbing up this index. And then, you know, Americans should be really fat and happy, but we see that we're really not much better than most of Western Europe, which uses substantially less energy. So we don't need to use American amounts of energy to be happy. In fact, Americans really ought to cut their consumption by a factor of 8. India is tricky because there's such a varied population and such a varied experience of wealth and poverty that this is really a bimodal distribution. If I were to plot out India, it would really be a mixture of stuff here and stuff up here. People living these experiences and people living these experiences. And so for 1.3 billion people, if the 300 million or so people in the US throttle their energy back by a factor of 8, but folks on this end of the scale, in India and China and other parts of the world that are developing, push up, even more energy efficiency in the US cannot compensate for this. And so the problem with this is that it directly correlates to how cheap electricity needs to be. And your energy in India is remarkably cheap. And it might not feel cheap based on how you need to spend money, but compared to the sources, compared to the battery itself, it's cheap. And we'll look at why this is a challenge in a little bit. So in the US, energy is about a factor of 5 to 10 more expensive. In New York City, it's about a factor of 5 more expensive. And then based on the subsidized price in Delhi, and I understand, I've been learning about India this week, I understand that this is a highly political number. And I won't say anything more about that. It's an exceptional number. If we had energy like this in the US for the first 200 units available, I'm not sure what would happen, but it would certainly make me want to vote for whoever gave that to me.
So disagreeing those numbers, Professor. Those numbers aren't correct for India. It's much, much higher.
So for Delhi, this is
So
what
it will be about 7 or 8 rupees. Or for commercial it will be 12 to 15.
No, so this is in cents. I convert it to cents. So this is, I should put the units here. This is for cents. So in cents, so this is 17.5 cents roughly in New York, depending. Comparatively in cents US, it's 4.5. Thank you for paying attention. So the reason why, no matter what your experience of energy is, the reason why I say it's cheap is because the battery costs the same no matter where you produce it in the world. There's tariffs and there's material supplies, but batteries, by and large, are a global product, and the price is set globally, much like oil is. And because of that, the best we can do to understand how the cost of the battery for the applications we want needs to fit into the tariff structure is we take the capital expenditure of the battery, we divide it by how many times we can use it. And this is a very basic, there's more advanced estimates of this, but this is the most basic estimate. You take this number, which is the capital cost of the battery. I go to the hardware store, I go to Amazon, I buy the battery. This is how many times I can use it. I divide this number by this number, and then I've converted from cents to rupees here. This is what the cost of using the battery every time is. And so the lead acid battery at best now doubles electricity. So electricity, I might say it's cheap, but because the grid is not as reliable as you want it to be, you're effectively paying twice that amount based on a current exide lead acid battery, and you have to replace this every 5 years. And so if we look at, I put skulls next to solutions that did not survive the market for various reasons. If we look at all of the available solutions, it at best adds, I've put the solutions in green that are cheaper than the current tariff in rupees, or at par with the current tariff. So if the, if it seems like this can fit within the tariff structure, it gets a green, and we notice that most of these in green have been failed in the marketplace, and we'll talk about why in a little bit. And so at Columbia, me and a team of other professors are trying to get to a system that's less than 1 rupee per use. So a very low capital cost and a very high cycle life, right? And so this is, again, the HDI index. The reason why we can't just burn our way out of this is that it's the same HDI versus CO2. The curve is the same. And so we're in this causal loop where in order to be more comfortable, in order to be happier, we have to, the way we make energy now, burn more fuel, which increases carbon production, which eventually will make it harder to live comfortably. So we have to break out of this cycle where we need to produce on the order of this much energy for every person, but we need to do it without the carbon dioxide production. Without carbon dioxide production at the same level. Right, so 5.5 tons per CO2 per person is unacceptable. 2,400, sure what these units are, 2,000 calories per day on an electricity basis per person is what we want to go for. And I don't think I have to convince this room that there's a direct correlation between burning things, CO2 production, and global warming. And so how do we continue to improve worldwide HDI without raising global temperature? This is the question. I think this is a really hard problem, but I think that once we solve this, and I think we can solve this, we are at a better position for getting to a true post-scarcity economy. So solar plus wind plus storage can get us there. There have been many studies capped by this very thorough investigation of the last 36 years of temperature data. This is in the continental US, but this methodology can be applied anywhere where there's been satellite data of atmospheric conditions. And so what this complicated plot tells us is that if we have 75% of our energy produced by solar, 25% of our energy produced by wind, we overproduce electricity by a factor of 1.5, so we have power production that is 50% greater than what we need, which turns out to be quite affordable. At this point, we would need 12 hours of storage for the entire grid to stabilize it to a point from generation, not distribution, but from generation, where the blackout period, based on the weather alone, would be 1 hour for every 10 years. Right? So 1 hour of no electricity for every 10 years of time from no fossil fuels, vapor. So this is an asymptotic, very hard target, but as an engineer, it gives me a target for how much storage I should produce. And so,
So when you say what we need, is that based on what comfort levels that?
that's a great question. No, so that's based on U.S. That's a great question. This is based on the continental U.S. So I think that this accounts for moderate but not excessive increases in efficiency. But it does account for electrification of transportation. So in the U.S., if you were to make buildings as efficient as you can, but then replace all of the fossil fuels in cars with EVs, roughly the impact on the grid would be a net zero. So this is a U.S. with a more efficient system at a high HDR. Maybe not to where Spain and Northern Europe is now, but close.
So the whole world at the continental US version.
Yes, which is the goal. Which is the goal. Whether or not that should be the goal, we can talk about over a beer. but we have to have a target with which to engineer a solution to work. So how do we get here? Let's talk about how good batteries are. Here's two apples, an apple and an apple. The apple on the left takes 2 months to charge, stores 100 calories and weighs 95 grams. The battery in this apple can be charged in 1.5 hours, weighs 20 grams, and stores 272 times the energy per unit mass as this. So batteries are significantly more energy dense than nature can do now. And I think that this is the only slide I need to tell me that growing crops and trying to feed crops to our devices is an exceptionally inefficient way. Electrochemistry, we should be eating these because I would rather be able to eat a nice apple than to plug myself into the wall. So we should plug our devices into the wall and we should be eating the apples and not vice versa. We would like to be a factor of 2 better than this in the amount of energy we can store per unit mass. This is an incorrect number for India, as I learned in some of my great meetings yesterday. So this is the U.S. want because we like our freedom and we like to be able to, or our illusion of freedom at least, and we like to be able to drive across large swaths of the country at will. We don't necessarily need this much battery, but even from a cost point of view, if you assume that per unit mass of battery, the cost is the same, then storing twice the amount of energy per unit mass should have the cost of the battery. So there's a good reason to have this target. We would like to be able to charge this quickly out of convenience. I'm not sure that we need to do that either. But there's a bigger problem that comes from the commercialization. I'm sorry, this got a little bit butchered, but Thomas Edison said in 1883, just as soon as a man gets working on the secondary battery, it brings out his penchant for lying. Scientifically, storage is all right, but commercially, as an absolute quantity, it is a complete catch penny, a complete scam. Thomas Edison in 1883. Why is this the case? So I like to invoke Tolstoy here. This is a learned room, so some of us might have read Anna Karenina, but you did not know that Anna Karenina was about a battery. The first line of the book, all happy families are alike, each unhappy family is unhappy in its own way. And it's why we can't currently have the battery that is cheap, stores a lot of energy, charges quickly, and lasts forever. So we have to pick what's important. If we look for perfection, we'll never be content. And if we don't appreciate these things, then we will be lied to and we will want to accept the lies, and anything is better than lies and deceit. So compromise is better than hoping for something that is impossible. And this is my engineering approach to batteries. And so there's empirical evidence, and I'm friends with the people that started these companies, and they did amazing things, and the technology worked. But there have to be very cold, hard looks at how one can apply the technology and what it can be useful for. So all of these companies folded and restructured, all had viable tech, and that tech has continued to be used. So the R&D efforts were not for naught, but the marketing somehow missed the target. And so now we're trying to learn from this round one of batteries by fitting into a given ecosystem and putting together a system for materials innovation, surface innovation, and packaging and separator innovation that fits into a sustainable ecosystem for storage. Lithium-ion has largely enabled this. But why is every battery unhappy in its own way? And there are a lot of reasons, and I teach an entire course on this. But here's a simple example. When we think about energy and power, it's hard to see a direct relationship between energy and power. Why can't I spend all the energy that I've stored in a given device as fast as I wanted to, or slow as I want to? And so when we think about a battery, we have to choose between energy and power even for a given chemistry. And the analogy I like to use, and I think that Mumbai is a great example of this because of the way your streets work, is that we can think of two ways of operation. And I use parking lots. Here you might want to think about streets. So if I have a parking lot and I want to maximize my revenue, I might say I want to store as many cars as I can in that parking lot per unit time. But if I want the convenience of being able to get my car in and out of this in less than half an hour, I need a parking that looks like this. So I need to, as the entrepreneur deciding how to design my parking lot, figure out what my customers need and charge accordingly. And if I don't, then even though I can store many cars here, no one's going to use my parking lot because it's not useful for that application. And the same is true in batteries. Within a battery, I have to move a significant amount of mass forward and backward. And because of that, I have to choose for a given location in that battery, am I going to store energy there, or am I going to have transport channels for that mass to move? The mathematics behind this can be quite difficult, but they're pretty well understood. But the other components of what we see in the trade-offs of battery aren't well understood, and this is where academics still have something to do. Why a system has to choose between the amount of energy it can store, how fast it can cycle, and how many times it can cycle is not well characterized. Why I have to choose between safety and cost is not well understood. And so I put all of these together in something I call the Unfortunate Tetrahedron. And it tells us that there is a trade-off between each one of these parameters. So Ravina asked me to make a battery that can do all of these, and I'm going to tell you, I can't. I can't because it's physically disallowed. Now, why it's physically disallowed isn't clear. We have empirical evidence. So between energy and power, I just explained it. But between capital cost and operating cost, how much, going back to that table, how much it costs and how many times I can use it, I don't have a good reason yet. And maybe we can do something about that. So we're within a factor of 2 to 5 for energy. We're within, we can maybe get to a 5-minute charge, but we are not going to be storing more energy per unit mass than we have now. Now, this is where I think things get exciting. How cheap can a battery be? So this battery is less than $20 per kilowatt hour. If you remember my plot before, this is 1/10 of all the other solutions that I showed you. But we can only use it once. And this is my favorite point. Why can't a battery last forever? And there's no good answer to that question. There's a lot of empirical evidence, but there's no physical law. So in a slide, I was able to explain the physical law between this relationship, but I can't do it here. And so there's no physical law that explains why cheap things can't last forever. And that's what I'm studying. So I came to Columbia to co-direct the Columbia Electrochemical Energy Center with my good friend Alan West. And we we put together a team of existing professors and new professors. We have 9 faculty that can answer every question in electrochemical energy storage, from the atomic design of the material all the way to how do we implement this. And you won't find a team like this at any other Ivy League institution. I know because I was at one, and Princeton's a fine institution, but they weren't going to hire 9 people to study this. And it's hard to find this at any other institution except for maybe MIT and Stanford. And confidentially, the battery engineers don't like each other at those places. So we're currently all friends. Hopefully we'll stay that way. These are hard problems. And so we cover everything. Some of us have more gray hair than others. And we cover everything from atoms to systems. And we're currently trying to engage with industry as opposed to government to understand what the limitations on adoption are. And so here is a brief history of batteries and my first crack at why cheap things might be able to last forever. If we look at what a battery has looked like for the last 200 years, it's had a cathode, an electrolyte, and an anode, and we separated these things in various forms to make them more useful. And over the last 200 years, we've explored the entire periodic table to see what can be useful. In fact, we started engineering batteries before we understood what the periodic table was, and then once we understood what the periodic table was, we knew where to look. And so every possible combination of chemistry has been tried. And we've gotten pretty good at manufacturing them. But there's some things that haven't changed in 200 years. And so there are 4 rules. The first rule is that this and this aren't supposed to touch. And 200 years ago, this was really important because there wasn't an electric grid at all. And so if you had a battery and these touched, then you wouldn't be able to use that battery in a week or a day or a month or a year. It was a primary power source. And so we wanted to maximize the shelf life. And then we wanted to balance energy and power. And then finally, the last thing was to make it rechargeable. This design, the least important aspect of this design is rechargeability. And so when you're trying to change the world, you have to question every assumption, even the most implicit. So here we're asking, can we reorder this? So that the most important thing is to make it rechargeable. Because remember, to make your electricity as cheap as it is today, while improving the reliability, we have to maximize the cycle life. So if this becomes the most important thing, and then making it last long, because your electricity in India might not be reliable, but it is there every day. You don't know necessarily when it's going to be there, but it's there every day. So this battery is connected more than it's disconnected. Let's leverage that. So why is this bad? We'll lose energy as heat. Thermodynamically, yes. Right? As a professor of thermodynamics, when these two touch, it will create heat. We'll destroy the battery. Well, that's because we've never designed it to do this. And finally, something horrible will happen. And so in the publications we've done around this, we've gotten rejection without review. Rejection without review because what you're saying is impossible and something horrible will happen. I went back to the editors and go, well, what? What is this horrible thing? And they said, everyone says it's horrible. And so we said, okay, we're going to do more studies to prove to you that it doesn't have to be horrible. And so what we ask then is, can this structure go and come at will? Can we control this and give up energy density and power density? Remember that we need to have these cars be able to move around the parking lot to get out. But what if I take that analogy a step further and say I'm going to reform the entire structure of the battery in every cycle so that every time I charge it, I reform it, and every time I discharge it, it fails completely. And instead of having to go in there and reformat the cell, I simply put electricity in. Electricity is my operating cost. And so we've realized this cell. So this movie is playing a little choppily, but this cell, the anode and cathode are constantly touching. And when the anode and cathode touch, they just discharge. I can always put more electricity in. And we cycle this cell thousands of times. We lose energy on every cycle. But remember that energy might be free. Energy is tending towards free. Your solar energy in India has to compete with coal on a tariff basis. And I said your electricity was pretty cheap. So if your electricity is cheap and the battery is cheap, all that's in this battery is 2 pieces of carbon and zinc and bromine. The Dead Sea is literally made of bromine, and zinc is readily available. It's an earth abundant material. And the rest is water. So, by most metrics, this is an awful battery. The energy density is poor. It doesn't stay charged for more than a few days at a time. If you take it off mains and you don't discharge the power, it will recombine. But for the job of grid-scale storage, where the idea is to use it as many times as possible and buffer daily events like wind and solar, it might be the best. So, back to Tolstoy, if you look for perfection, you'll never be content. So, this is more for fun than anything else, but it turns out we're able to do something with this. So I tried to recharge that AA battery many times because it's $20 per kilowatt hour, and it was a Sisyphusian task. It is, if not impossible, really hard. So I know every way a AA battery could break, and I spent like a couple $1 billion in taxpayer money to do this. And my friends weren't thrilled about this because they said, "Oh, I could have told you that battery can't be recharged." So then they said, "Okay, you have to answer an important question then." I saw this video on YouTube. This video on YouTube said if I take a AA battery and I drop it when it is So I take this AA battery and I'm sorry. Okay. What are we going to do? The video was okay. So
Yeah, it's working now.
Okay.
It's working on that.
it's working on that. It hasn't. It's not up here. Can you stop the presentation or restart it? Stop the presentation. Starts. Yeah. Yeah. It's not.
It's not connected to that. Maybe, is it because of the takeoff?
There we go. Okay. Round 2. So
Yeah.
here we go. So this is a real experiment. If this battery is new, it won't bounce. If this battery is fully spent, it will bounce quite high, but you'll notice that we have this nice curve. If this was a straight line, this might be worth a senior thesis or a master's thesis. Because it's not linear, it was able to produce a few PhDs. Why does this battery bounce, and what can we learn from it? And it turns out that by studying this behavior, we found this fundamental link that people hadn't seen before in batteries, that sound, right? So what is a bounce but tapping the battery? The battery is dumb, it doesn't know whether it's dropping or the table's moving up. And so if the table's moving up and hitting the battery, then it's a dynamic strain event, and the gentlest form of dynamic strain is sound. So we then asked ourselves, is there a fundamental link between sound and the state of a battery? And it turns out that there is, and it's quite strong, and it applies to all batteries regardless of their chemistry, whether they've been invented or not. And so we launched a company called Feasible, and Feasible is a joke name because people were like, oh, sound has nothing to do with batteries, and then a minute later after I showed battery engineers all the equations, and they said, well, sound has to have something to do with batteries. So the idea is that it's feasible, but it's also the government, when it gives you money, likes to have acronyms. So it stands for Fast Electrochemical Acoustic Signal Interrogation for Battery Lifetime Enhancement. And that's why I get government grants. So it turns out that by measuring the acoustic response of a battery, you have two ways of understanding it. One is just to understand the physics, and we're still working on that in the lab. But even if you don't understand the physics, you can feed the data into fairly standard machine learning algorithms and back out the state. So if you understand and have the ability to measure the sound reliably, then the acoustic signature gives you a strong signal of how good the battery is, how old the battery is, how charged the battery is. And we published a few papers on this, and Feasible is doing just quality control and quality assurance of batteries, and maybe they'll move into battery management systems. So we've learned a lot of lessons in this space, and we learned to focus and integrate. But the big question is, and the question I can't answer you right now, is that will this lithium-ion tool chain, because all of these companies are built around lithium-ion, will this lithium-ion tool chain get us to this point where we get to the number we need to get to really stabilize the grid and enable a post-scarcity economy? I'm not sure it is, so we're looking at this radical approach to what a battery can be by letting it completely destroy itself to reconstitute it, trading off energy density and power density in the process. Thank you so much for your time dealing with technical difficulties.